Welcome to the Bytecode, where we look at smart contracts with the people who wrote them. I'm your host Shafu, and today's episode is with Maurelian, who's going to walk us through the Optimism Bridge contracts. Maurelian, thanks for taking the time, man.
Yeah, happy to be here, Shafu.
Shafu, yes. Awesome. So, yeah, why don't you briefly introduce yourself? I don't think you need to introduce Optimism, to be honest.
Yeah,
But yeah, briefly introduce yourself, what you do, and then we can start looking at the diagram and then jump into the code.
sure thing. Yeah. Um, so I'm Maurelian. I am a protocol security engineer at Optimism, uh, where I've been since 2021. Prior to that, I was a co-founding member of Consensus Diligence, the audit firm at Consensus.
Awesome. Sounds great. So yeah, you're gonna walk us through the Optimism Bridge contracts, right?
Great. Yeah, let's do it. So what I think is like the most valuable thing to do with this time that I'm excited about is to create like what I hope will be a useful reference for people that actually do need to understand our code, uh, which is a lot of people, obviously. And I think like the most security critical contracts are our bridge contracts. What I'm going to try and do is walk us through at least at like the life cycle of a deposit from L1 to L2, and hopefully also a withdrawal uh, from L2 to L1. And so my goal is that with this you'll have like a high level sense of how the pieces fit together, some of the threat model, and ideally for me as a security engineer, this becomes a resource for security researchers who are looking at either our code base or a fork of the OP stack, which is increasingly common. So it's been really interesting for us to see this like ecosystem of experts in our code emerge. Like I'm seeing auditors be in demand for their experience with our code so that they can work on things like the Blast competition or Frax code base, other projects. So, anyways, I'll get into the code without further ado. So I prepared this diagram. It's a little busy, I will admit. But I'm gonna try and just give like a high level overview of the architecture, and then we can jump into actually looking at the contracts. So, um, I'll try to like break this down. So before we talk about the deposit and withdrawal, what I want to do is like say like demonstrate or like impart upon people that there's sort of like an onion as I see it of with these different layers, not like L1 and L2 type layer, but like of layers of abstraction in like what in the way that L1 and L2 communicate with each other. So the inside of the layer is consists of this optimism portal contract, which is
Yeah,
go ahead.
Maurelian, could you maybe zoom in a little bit more?
Yeah, for sure, for sure. Yeah, my
Awesome.
screen is large, so it's big for me, but not necessarily for everyone else out there. Yeah, so we have this optimism portal. It's what you call like when you want to make a deposit, you're gonna call it. When you want to finalize a withdrawal, when you're actually like making a withdrawal from L2 to L1, you also go through the portal. Importantly, the portal I should feel like I should add this. It's like uh it holds the ETH. So like there's a big it holds the ETH, not the token, so it is a big uh honeypot, uh, if you will. And then like on the opposite side we have this L2 to L1 message passer. It's also like at the inside of the onion. It's only involved on the withdrawal path for like reasons that we'll get into. Um, we also have this L2 output oracle, so it basically like holds a representation of the L2 state. In particular, it holds the state root of like which commits to the entire state of L2, the L2 system. It also holds the specific state root of this contract, and that helps to facilitate withdrawals. Um, then it's also important to say that it's not just contracts at the inside of this layer of this onion. There are also these. They're not just Go. You could write these services in other languages, but the first languages we use were Go. So there's these important client services, node protocol software. One is the OP node. The other is OP geth. And so what the OP node does is it reads the events emitted by the Optimism portal, and it actually translates those events into transactions that happen on L2. So it kind of like often for somebody coming to our contracts for the first time, there's this gap because they're just looking at the contracts and they'll look at some of the L2 flow and think like where is this coming from? Where do these transactions emerge from in the deposit path? And it does feel a little bit magical, which is, I mean, it's still, to me it feels a little bit magical, and that's part of the awesomeness of the system. So I think like, and then I mean, to like I won't talk too much about, but then like we have, so this is like a very low level layer that you can interact with directly. Most services are going to integrate the L1 and L2 cross domain messenger, and so that's like there's a specific interface that your contract can integrate with to send data, uh, messages, as well as ETH from one chain, from L2 to L1 or L1 to L2. And there are these bridge contracts where tokens are actually stored. So if you deposit USDC here, it will be held here, and then like the messages will flow across, and then USDC will be minted on L2, and like at the correct USDC address, and then it can be burned and returned back through this flow. So I think that that's like a reasonable high level overview. We'll come back to each of these concepts as we go through the code. So and I'm gonna just like refer to the doc that we put together in advance of this. Yeah, so I'm working like, I don't know if anybody cares that much, but we'll be working on this v1.2.0 tag, and the specs repo is, I've just linked to it here, but yeah, so that's what I need to see. So this is our monorepo. There's a lot of stuff going on in this repo, but where we're gonna spend most of our time is in what's called contracts bedrock. Really, it's just all our contracts. Bedrock was the name of our major upgrade almost a year ago now, and it's sort of just, we haven't deleted the bedrock term from that yet. So I said I was going to start. So where I'll start first is the Optimism portal, just so you can follow along. We're going to look at the Optimism portal, and then I think we'll probably look at the op node to see how that's picking up events. So again, we're continuing with the deposit path, how value and data gets from L1 to L2. So
Yeah, could you again zoom in a little bit?
oh yeah, of course. How's that?
Awesome, thank you.
Okay. I'm gonna turn off the blame, the line blame. Yeah, so that we don't. All right, so yeah, I'm gonna skim over a lot of this stuff. But so this is our Optimism portal. It's initializable. We do use upgradability. It has this resource metering code that we'll look at a little bit. and then assembler, which is just kind of an internal versioning system that we don't need to get into. You have your constants here, references to other contracts in the system. This stuff is mostly withdrawal oriented, so I'm really just going to jump ahead. Okay, so here we define an event, transaction deposited. When this event is emitted, it basically the intent is that it contains everything that you would see in a typical L1 transaction that you submit from your EOA. So let's look for where that actually happens. We have this deposit transaction call. It accepts deposits of ETH and data and emits a transaction deposit event for use in deriving deposit transactions. If a deposit is made by a contract, its address will be aliased. I'm going to skim over that for now. Maybe we'll get to it when we get into the code. And then we have this kind of little consider using the cross-domain messenger contracts for a simpler developer experience. This is we like to underscore that this is probably a very powerful this is more powerful, more flexible code here. But there's also some foot guns that you need to be aware of. So it's really caveat emptor here. So yeah, as you're calling it, these are the kinds of arguments that you would typically expect to see for the most part with a typical EIP 155 transaction. So you specify the address that you want to receive, use the amount of ETH, the gas limit for the L2 transaction. This is not normal, but we we need this Boolean. So is creation means you'll actually be creating a contract. So the data that you submit will become the init data for for a contract that you are trying to deploy. So you can actually deploy a contract on L2 from L1 using this method. And the reason we need to do this is because if I remember correctly, with a typical transaction, it is if you want to initialize a contract, this would be null. You would make 2 null. We don't really have a null value. It should be valid to set this to 0. So because we don't have a way of making that empty or null, we have to have this Boolean to indicate that we want to create a new contract. We go through here, we do a check to make sure that you're not doing both those things. If you specify a recipient address, then there's no reason that you would want to also be creating a contract, deploying a contract on L2. We require a certain minimum gas limit. We check that your data is not too large. And this is basically protecting the bandwidth of our network. Okay, and so now we can talk a little bit about the aliasing idea. So what we do here is we actually do this much maligned message.sender does not equal transaction.origin check here. It is not a security thing, and we don't want to hear from you if you think that this is the wrong thing to do. Basically, what we're saying here is if you are calling from a contract, then we're going to alias your address. So when the address appears on L2, what we'll do is we will shift the we'll do some math rather, but we'll apply this mask and bump the upper and lower bytes by these values, by this 1111. And the reason for this is kind of subtle, but the idea is when you're going in through the portal, which again is this low level thing, there's no contract. So if a contract calls the portal, it's going to go through this magic path. It's just going to appear as a transaction. And so there's no way to actually know that the transaction is originating on L1. And so what you could have is that you can have contracts at the same address on both L1 and L2. Let's say that they're a wallet or like a Gnosis safe. So if we have a Gnosis safe at L1 and L2, which you may want it to own you may want the L2 wallet to own your contract and be authorized to take certain actions. But you don't necessarily have the same state. So even though you have a Gnosis safe at the same address on L1 and a Gnosis safe at the same address on L2, doesn't mean you have the same signer set. You may have, it may have drifted. So you don't necessarily want the auth tied just to the address. This gives you a way of ensuring that you are in fact getting the call from the L1 Gnosis safe by checking that it is aliased properly, or from the L2 Gnosis safe by validating that is the expected address there. And we know that you're not going to be able to find, deploy a Gnosis safe or find the private key for an address derived by this aliasing, because that's just too hard, and we depend on that cryptographic security for everything in our system. So that's the alias. Okay, and then what we do, we do a little bit of packing just for gas efficiency. I slightly regret this. I think it probably doesn't save us that much gas, and it does make the actual transaction, it would be nice if you could just sort of read this and parse it. It would be easier to read if we weren't encoding this opaque data. But basically what we're doing is we're taking the arguments that you're going to need to derive the transaction on L2, and we're pulling them out and we're putting them in here. And so this is going to be emitted, and then we're going to read it in the op node. I'm just going to look at the Google Doc, pull out, so deposits.go, depositlog.go. What do you think so far, Shafu? Any gaps, anything not making sense?
Yeah, I didn't fully get why you have to shift the address exactly, to be honest.
Yeah. It's why you have to shift the address. Okay, so what about the Gnosis safe word? Because I talked a lot about it, so I want you to tell me where the gap is before I jump into that long story again, or try
I
to...
understand that you could have a contract on L1 and L2 that have the same address but different state.
Yep.
That totally makes sense. So the issue you're trying to avoid is that you basically are trying to access some kind of state on L2 by deploying something to that exact address.
Yeah.
And you're avoiding that by basically changing that address to something else.
Let's just say you have a basic only owner function, and so it's only owner equals, let's say our address, you and I have a multi-sig and it's at address 0x20. So your only owner functionality is going to say require owner equals 0x20. But let's say that I have a multi-sig on L1 that just I own, but it's also at 0x20. So it's your intention with that only owner check is to ensure that you and I have both agreed to make this call. But if we didn't do this aliasing to basically then we're leaving it open for me to simply submit this transaction from L1 to L2 to like get past the only owner check.
Hmm. Okay. Okay. Yeah, I think I get it now.
It's a bit of a trip. Like I had to think about it a fair bit.
Hmm.
I'm trying to think where the place to go. I mean, this is not a bad time. I think the move now is to just like tell people where they can learn more. Um, so like our specs repo, great repo. Very like we use a spec driven development process, and we try to write our specs as much as possible before actually building anything. And so in here, there's a whole section that gives the like the justification, I think, pretty effectively. So maybe I'll just like I'll pop that into the doc so that you can share it if you want to later.
Yeah, that's a great reference.
Let's see. So what we're doing. So this is our OP node. And this is code that is going to again. So here's like a little bit of inline solidity. And so it's referencing this event that will be emitted, and it's going to decode the arguments in the event log and extract them. Um, do just this extraction, and it will return. I mean, basically, it's going to return a deposit ticks type, which looks like this. So it has like your proper from, to, mint, value, gas. This is an extra thing that we don't need to go into. Well, it indicates that it's not a signed transaction. So so this is important in that it's like a separate auth model or for validation of the transaction, um, and your bytes here. So because it's a system transaction, it means that the node can pick up, can like create this, and the sequencer can attest to the validity of this deposit transaction. And then we could, I think, like I'll skip going to OP Geth, but hmm, I can go that quickly because I want people to know where to find this. It is pretty interesting. For those who are like to go through Geth. There's like you can find the diff here where it actually handles a deposit transaction. And the like it's worth looking at the distinct um like logic that is introduced for that. It's also worth noting that we work very hard to minimize the diff between upstream Geth and our Geth, to the extent that we um, credit to Proto Lambda for creating this site. Actually have like this site that breaks down all of the diff. So it actually just like describes why that diff exists. I'm not sure like what that exactly shows. Yeah, it just goes here, but still like every diff from OPGeth to the upstream is documented in that site.
That's a great site.
It really is.
Um,
Yeah, I
uh,
use
ju-
it all the time.
just a question: is the difference between OP Geth and Geth getting bigger over time or smaller? Because looking at that page, if I remember correctly, like a couple of years ago, wasn't like the difference like 500 lines of code or something? Or am I remembering that incorrectly?
It was smaller. It is growing. It
Okay.
it went so we used to have a whole other so prior to the Bedrock upgrade we had like this we had L2 Geth, which is a whole other service. It lived in our monorepo. And so I would say like the diff was huge. It came way down with OP Geth, and it's creeping up over time because it's becoming more like L2 has I don't know, we need features. We need to do stuff, and it does more and more useful stuff all the time. I can't like think of exactly like what some of those things are right now. Yeah, so I mean, for like we're introducing, 4844 support. I think that's a pretty small diff in Geth. We also, but like spam batches? No, that's an OP node thing. I'm not super close to like the day-to-day of OP Geth, to be honest with you.
Yeah.
So I'm going to, let's see. I think I'll continue with the like the moving through the bridge flow. So what we've done so far, we've talked about the portals, deposit transaction, OP node, OP Geth. Probably good to look at the cross domain messenger on L2. So the L2 cross domain messenger is a rather thin wrapper around a lot more logic in the cross domain messenger, like this abstract contract. So we've got nice symmetry between the L2 and there's another L1 cross domain messenger, which is like similarly boring, like this one. And this is sort of interesting. This is like just pure tech debt, but basically like what we do to block out, like we've done upgrades, we've removed things from the state over time. And so whenever we do that, we add in these like spacers that actually call out what used to be there. And so I kind of think of it like scar tissue because these like I would like to maybe at some point start like reusing that space. Like we're like, okay, it's empty. We need a new argument. Let's just like put it in there so we don't have to keep these spacers there. But for now, we're just like we're very conservative about that, and we keep it that way. I kind of want to like, yeah, I think like another interesting process item that we have is these layout locks. So, like related to that is that we check this in, and so like this I forget exactly how this is generated. I think it's a forge command of some sort that like creates this JSON. I believe Sol-C actually outputs this, and so like this is same file. So you have an address argument. It's the 0th slot of the contract. It's 20 bytes, offset 0. An initialized, so that's 1 byte. It's at offset 20. It's a uint 8. So any PR that is going to change your storage layout will actually like require that to be checked into the commit and go through PR review, and somebody will be like, why are you changing the storage layout? So that's I think that's like a nice piece of process we have. We also have tooling in our upgrades to validate like state changes or like storage layout changes as well. So anyways, yeah,
Sol-C generates the JSON.
I believe so. I think it's like
Okay.
storage layout. I don't know. It'll be in our scripts somewhere. But I said we were going to look at since we diverged slightly, resetting, we're going to look at relay message in the L2 cross domain messenger, which is what gets the data and the ETH into L2. So send message, that goes the other way. We can skip over that for now. Relay message. So basically, there are two ways that this function gets called. One is the happy path where it's the deposit transaction, the special system transaction type that we've talked about, where that gets inserted. It provides these arguments. These arguments are actually encoded by the L1 cross domain messenger. So I do actually think like so rather like we're like unwrapping the onion a little bit. So instead of just following the line, let's like unwrap the onion. So let's go think, okay, L1 cross domain messenger called deposit transaction on the Optimism portal. We went through these services. Now we're calling the L2 cross-domain messenger. So we can actually like think, okay, the L1 cross-domain messenger like is where we're starting now that we are stepping out to the higher level messaging abstraction layer. So remember, so this is like holds all the logic. Imagine that we're actually, well, let's go to the L1 cross-domain messenger. Yes, so we call send message. So this is imported, inherited into the L1 cross-domain messenger. You call send message from L1. It basically wraps this send message here, which is a call to the portal deposit transaction. So it's going to forward. It's going to forward the value. I'm sure there's a message.value check somewhere here. It looks like it just blindly takes your argument. But I would have heard about it by now if we weren't validating that somewhere. So where does that happen? Oh, so it reads. That's interesting. Here it actually. Okay, yeah. So it calls. This is a call to this send message. So here it takes the argument, but here it is actually like setting that argument based on the like what is it, call value or value opcode. Okay, so cool. We do that, and we encode in that call. We encode. Well, we like set a gas limit that it's like you're gonna need at least this much gas. So we make sure this is the L2 gas. We make sure that that's included, and then we encode all these arguments to the relay message. So the L1 cross-domain messenger is literally saying, "Hey, portal, I want you to take this data." So this here is the, if we were using Quark syntax, which we should be here, this is the data argument. So, hey portal, I'm going to send you this deposit transaction with this data, and I want you to call the other messenger. So like my twin, my counterpart on L2. And so that's going to happen. It's going to call relay message in the L2 cross-domain messenger. So we come down here and we check that it's not paused. We have a like pausability system that is actually almost worth a whole conversation. But we will gloss over. We have, this is like a versioning system in case we ever change the cross-domain messaging, like the format of that message to have a new encoding. Because we have in the past with the Bedrock upgrade, so we had like a pre-Bedrock versioning message, which didn't have value. You actually didn't have the ability to deposit ETH through this path. You had to do something else. But the vast majority of systems are going to be using to have version 1. V1 meshes hash. So if version equals 0, we do a check here. I'm fuzzy on this, so I'm just going to skip over it. There's a lot of checks we could talk about. This is a tricky code path here. Basically, so I said there's sort of like you're coming in from a happy path, or you're coming in from the happy path having failed. So that's, replay protection. So we have this system whereby if you deposit, like your L1 to L2 transaction comes in and it's calling, like you're trying to mint an NFT, and you go through the cross-domain messenger system, if that mint fails for whatever reason, if it comes back at like status failed, then it gets added to this failed messages, was that a mapping, and it like allows you to attempt to replay it. But so we do this is other messenger check. This tells us it's like basically a system transaction coming in for the first time, in which case we require that the ETH is there. and we require that it has not already been like written into the failed messages mapping. Otherwise, we require that there's no ETH being sent, and the ETH is actually already stored in this contract, and we're just going to look up the message, the hash of the message in this failed messages mapping, and then allow it to be replayed. I don't love this flow. It's kind of hard to read, but it's like held up for a long time, and I think it's super solid. I think like some interesting things in here. We chose to we have these checks. We used assert because that in my opinion connotes like this is like we should never ever hit this. But we're calling that out, and we don't want to like omit the check just to save some gas or something like that. So we're including that. But we expect that this will never ever come back false. It should not be a reachable code path for the first time that this is tried to not have value included with it. What is this? Yeah, and this so we're checking both like up here that so assume we're on the first try. We'll forget like we'll avoid talking too much about the replay path. Happy path first time in, we say okay. This hasn't already been tried, and so like it's the first time. And so we also validate that it's like not already been executed successfully here. Then we do a lot of work to check some invariants about gas to make sure that it's being forwarded with the amount expected. And then we and then Hasmin gas they call it. So this is just a gas check. Well, this is a funny little code path. I think like yeah, if it doesn't have enough gas, we'll just fail right away. Is basically what we're doing here, and then we'll return. We also have this little branch that allows for gas estimation. So this is like some maybe it's the zero address or something like that like nobody owns, and so you can submit the call with the from address as that address just to go through into this path, and this like helps with gas estimation. So if you don't have enough gas, then like you'll trigger this will be true, and you'll go in through here, and then the gas estimation, which uses a binary search, will like bump up the gas and keep trying until it can like move through and actually like get to the successful path. I see you like squinting, Shafu.
Yeah, that's the first time I see something like that.
I know. I don't like.
Oh,
I don't know why I've never seen this. Why do we need this? I don't know. And like I feel uneasy about it. But straight up, like I don't know. What do other people do? I don't know.
okay. Yeah, yeah, I've never seen explicitly uh, that someone put something explicitly in the contract for gas estimation. You know what I
Yeah.
mean?
Yep.
Like for external services to do the gas estimation. So that's the first time I see that.
What is it like? Why would this not um what would not work if we didn't do that? Well,
Like
there's a
if you
big comment here,
remove
so
if you remove the transaction origin equal to estimation address, like what difference would it make if that wasn't there? Okay, you don't have that revert message, but your transaction would still just revert, right? If you don't have enough gas.
yeah. You go well okay. This is why. It's because it is because what we want to do is not revert. We don't want to revert. We want to return. We want to queue this up for a replay. We want to write to this mapping and say you're welcome to come back and try this again and submit more gas next time. If we revert here, then we're not providing replay protection. And you cannot, because this is a deposit transaction, it's a system transaction, you can never try it again. So that is like the whole purpose of this cross-domain messenger layer, is to provide these like replayability guarantees. So if we simply if we don't do this, if we just go like this, then this won't stick. So we're trying to help the gas estimation. What it is if you don't provide enough gas, but we don't do this, you'll succeed. Your transaction will succeed, but it won't actually have been like successful. It will succeed in becoming replayable. But that's not what, there's like variations of success here, which are like more than just 0 or 1.
Okay.
Yeah.
That's that's definitely interesting.
Yeah, I'm glad I was able to remember what that was about, and not just kind of look silly. Okay, so super important, interesting stuff happening here. We are setting this state variable. It's a public state variable. There's a getter up above for it to the sender argument. And then we're going to forward the call to the target with like enough gas. We keep some gas back so that we can do this like extra bookkeeping after. And so safe call.call is, I don't want to go into too much. It's a wrapper around call basically, and it is memory safe, I think is what this does. So yeah, so it does not read the return data, because there's this memory bomb attack, or where the contract can return like an unlimited amount of data, and then like just like we read it, and our state, or I guess our memory size expands. The cost expands quadratically with the size of memory, and we're going to fail, and we can't really prevent that. So we've built that in here, and so this is, but like read this basically as like call to target address target.call. So the semantics of this are that earlier I said with our cross-domain messengers, contracts need to integrate them. So they need to be aware of it. They basically the main thing is that they need to read this X domain message sender variable to for like auth, or to like determine who the call is coming from. So you can't really use, so what you do for that is we have these sort of contracts that provide this this functionality for you. So nope, that's not. Is that the right one? Yeah, no, this is not. We have 3 of these for some reason. Yeah, so this is the one that integrates with the messengers. The one I was looking at previously is like the low-level layer that just like works with the portal. But so this one will basically, it's going to validate ownership by saying, okay, is the call coming from the messenger, which we've been looking at? Yeah, so is the call coming from this contract? Yes, okay. Then is the owner equal to the X domain message sender state variable that was set before the call? So if we jump back in here, so we set this state variable to the sender. The recipient contract can read this variable, and we call the target, it reads this variable, and then when that's done, as soon as that's done, we reset this to the default L2 sender, which is Not the 0 address, but again, some address that nobody owns and isn't worth looking up. And then if it was successful, we write it into the mapping, and if it failed, and we say so successful, it cannot ever be played again. And if it failed, then we queue it up for replay, basically. I want to like show this line. It's like again an assert the expectation. So basically, like it's simple but like powerful. The idea is that we used to not have this line, so it was just okay. The call came back successful, so great. We'll write it here, and that's fine generally. But adding this is like we make sure that this isn't already true. Like the invariant being, we do not want two successful calls. We don't want the ETH forwarded twice. That's like the fundamental thing we don't want to allow to happen. And so this is like credit to the auditor trust for identifying this like small improvement, which honestly is one of my favorite lines of code ever, because it's just like it's so obviously we don't want to write true over true, um, but we had not like stopped and thought about how we could prevent that. So another way of putting it is that I see this as being a little bit more of a, I don't know how to pronounce this, but like the free pie pattern where we're checking our invariants after execution to ensure that like we're still good. We hit this estimation address again. So there's it's a twisty code path. I don't love this code path, but it's like it's it's been looked at very closely by a lot of people. Um so generally we don't touch this in the sense that you don't touch it. Um because it's dangerous and we don't want to mess with it, and it's working. So where did we get to? And how are we for time?
We have 10 minutes left.
We have 10 minutes. All right. So yeah, we got like through from here to here. And I think the bridges are kind of boring. They're just like wrappers around this messaging layer. You put a token in, you get a token out. Uh you deposit a token here, you mint or burn a token here. We have support actually for going the other way. So you can, if you have an L2 native token, you can also create an L1 representation. And so it's a bidirectional bridge. But probably what's more interesting to touch on, yeah, definitely more interesting, is to think about the opposite direction. So I'll cover that like high level in 2 minutes in the diagram, and then maybe find like the interesting piece of code. Um, sorry about that beep. That's my calendar. So yeah, so we're gonna call this L2 to L1 message passer with our withdrawal. It's basically like it's gonna write a hash into its state, which represents that withdrawal. In a very similar way to the event emitted here encodes the arguments for the the system deposit transaction. The arguments that go into the hash stored in this contract when you initiate a withdrawal are going to be the representation of the transaction on L1. But because we're on L1 and we don't have magical OP get, we have to do this all in the contract layer. So good news, Solidity heads, there's no more Go code. Or at least like I won't walk you through the proposer because it's not that interesting. So you like put this commitment to your withdrawal in L2, and then the proposer is this service that it basically just reads the state of L2 and it attests to it in this L2 output oracle. So the L2 output has like 4 arguments that all come from anybody can just read from the from their L2 node. and they can see that they are correct. But the proposer actually has permission to write them to L1, and then that information is used when you want to forward your transaction. So the transaction is created on L2. You actually have to get it through the portal. So you go to the portal, you provide the arguments for your transaction. It's going to read the L2 output oracle, and it's going to validate that that transaction was in fact created with those arguments on L2. And it does that and so that all happens like fairly close together. I'm calling it in this diagram like proving time. And then we have this like finality delay of currently 7 days, and after that 7-day window has passed, you've proven your withdrawal. Wait 7 days, and you can come and finalize the withdrawal. So this was a big improvement. I think it's also somewhat unique in the rollup space that we have this two-step process. It's a bit of a UX hit, but it is massively, massively more secure, because the kind of attacks that we've seen on, I believe it was, I forget, there's been a couple Binance chains, but like, I think it was BNB chain or something like that. And Polygon has seen like similar withdrawal attacks in the past, are basically Merkle Patricia try spoofing attacks. So do I just talk shit? Would you like me to talk about that class of attacks, or like walk through this code path a little bit more, Shifu? What's your thought?
Yeah, let's look at the implementation for the
Cool.
last couple of minutes, I think.
Sure thing. So we're back in the portal, as I mentioned, and we'll also want to look at the oracle. That's the wrong. So, as I said, I think the thing to do is like be aware that we have this array of output proposals, which are coming from this proposer service. So what's in an output proposal? That's the wrong one. An output proposal contains, I guess I was wrong, it has 3 values. It has an output root, which is like the full, wait a second, output root. Is it really just the message pass or storage root? Hash of the alter. Yeah, it looks to me like it's actually the like output of the full L2 state. I was quite sure. I don't know. Let's see how it actually gets used. So the portal. So when we come to the portal, and we're gonna go to finalize. No, we're gonna go to prove. So you prove your withdrawal transaction. You submit the arguments. This is basically just like, again, it's from and to and all those arguments, and so we take these arguments, we get, and you also say which output index to get from the oracle, and you get the output root from it in particular. And then you also have the output root proof and message path. Okay, so the storage root is in this proof actually. So what we're doing is you're basically like, all right, okay, so now I know what it is. This output root is a hash of these values. So it's a 32 byte attestation to these values. And this is the full L2 state, and this is the state of the L2 to L1 message passer. And so then like with that state, you can prove that you take your transaction arguments, and there's actually a call to our Merkle trie implementation. So you basically are proving that the withdrawal, which is in the L2 to L1 message passer, is in its state by providing this proof. So once you've successfully proven that the withdrawal transaction was created on L2, then it is you're written to the proven withdrawals mapping with a timestamp at which time for the time it was proven, and then when enough time has passed, you can come along and forward it, and it does a lot of stuff similar to the cross-domain messenger. Like if we just go, like we probably have the same estimation stuff going on in here. We have the same like safe call coming from here. There's a different security model from the portal because we don't have replay support. So it's just like you better have specified enough gas on L2 or you're in trouble. Because it's like the lower level thing. So it does look a bit different, but generally like, yeah, you set your sender, contracts integrate with the portal, they read it, we send the call, we set it back to the default, emit event. Yeah, and so I think like maybe just to quickly recap, we've kind of gotten through a lot of this. I would love to have touched on the Oracle more. It's pretty simple. There's a lot of nuances to get into the withdrawal path here. But that should, I think, serve as a good like 101 primer for anybody trying to get a foothold in the bridge code base, which can be fairly daunting for people at times.
Yeah, definitely. Yeah, thank you so much for this walkthrough. Obviously, the Optimism Bridge is a piece of infrastructure that that gets executed a lot. So yeah, great overview, great diagram. If you could send me a link to that diagram, so I
For
can
sure.
put it in description, that would be awesome. Obviously, I would put the Optimism monorepo in description, your Twitter as well. Other than that, something I should link to. I think
I think that's good. If
that's
people
good.
want to find me, usually like my primary channel these days is on Farcaster. It's
Okay,
maurelian.eth, maurelin.eth. And yeah, I think like the main resources are the monorepo, the specs, and this diagram that we will link to.
perfect. Then yeah, thank you again, and thanks for tuning in, guys. See you in the next one. Bye bye.